I hate to break it to you, but we don't have all the answers. Here's a mystery of nature that remains unsolved to this day. Although maybe that's not such a bad thing. It means physicists of the future still have some work to do, and perhaps you could be among those who eventually find a solution to this puzzle. Inertial mass versus gravitational mass. Two different properties of matter, very different properties, that nevertheless turn out seemingly coincidentally to always have exactly the same value. And no one knows why. We have encountered two different properties exhibited by all matter. One, matter resists a change in velocity. In other words, matter possesses inertia. Two, matter experiences a force when in a gravitational field. These are two very different things, and yet we call both of these properties mass. Let's instead give these two things two slightly different names. The thing we'll call mass in Newton's second law could be renamed inertial mass because it is a measurement of an object's resistance to acceleration. Likewise, the thing we call mass in the law of gravity could be renamed gravitational mass because it is a measure of how strongly an object interacts with the gravitational field. So let's imagine taking an object, the same object, and setting up two different experiments, one to measure the object's inertial mass and one to measure its gravitational mass. Okay, experiment one. We have a simple block here, and we'll put it on a frictionless surface, pull it with a spring scale here, and measure the resulting acceleration with this motion detector. With the spring scale, we can measure the net force acting on the object. The block will accelerate along the surface. And then, applying Newton's second law here, we can calculate the so-called inertial mass by taking the net force magnitude and dividing by the magnitude of the acceleration. Okay, so that's a way of calculating this property, this resistance to acceleration, the inertial mass. Experiment 2, we'll take the same block and just place it on a scale. I'm placing it on an electronic balance here. The readout there is going to tell us the magnitude of the normal force acting on the block, the contact force from the plate pushing up on the block. But since the block's at rest, of course, the normal force is equal to the force of gravity. In other words, the apparent weight of the block is equal to the weight of the block. And then Newton's law of gravity tells us that we can calculate this property, the gravitational mass, by dividing the magnitude of the force of gravity by the known magnitude of the gravitational field. In other words, divided by the gravitational field strength, little g, right here. Right there, we are using the law of gravity. Okay, so we've calculated m inertial and m gravitational, and what we discover is this. Although these are two very different properties, there's no reason to expect that m inertial and m gravitational should come out to be the same number. Yet such experiments always produce the same result. For any object made of any kind of matter, its inertial mass and gravitational mass are always exactly equal. Physicists do not yet understand why. These two logically different things are apparently the same thing. It remains one of the unsolved questions of modern physics. In practice, we generally ignore the difference between these two quantities and just refer to both of them simply as mass, m. That's what we'll be doing from here on out. We're kind of ignoring this, we'll be ignoring this puzzle. But let's look at an important consequence of the apparent equality between inertial mass and gravitational mass. Consider an object in free fall. Let's take that block there and just drop it. So it's in free fall. The only force acting on it is the force of gravity. And putting together Newton's second law, in which the net force is just the force of gravity, and the law of gravity here, in which we replace the force of gravity with the gravitational mass times the gravitational field, we can calculate the acceleration. Here, since gravitational mass and inertial mass are apparently always the same thing, they cancel, and we're led to the conclusion we've previously drawn from our observation of falling objects and projectiles. All objects in free fall have the same acceleration, little g. The acceleration of the object ends up equal to the gravitational field because of this cancellation. We can think of the result this way. The more massive an object is, the more strongly it is pulled on by gravity, tending to cause a higher acceleration. Bigger gravitational force, bigger acceleration. But also, the more massive the object is, the more it resists that acceleration due to its high inertia. So these counteracting effects cancel. Thus, the acceleration of an object in free fall is independent of mass. Always comes out to that value, the strength of the gravitational field, due to this mystery right here.